my name is Guang, 13 years old. For this lesson, we'll be continuing on with definite integration for Green's theorem. So for the previous lesson, we have solved the first case for this part, for this listed different cases. So to begin with, over here we have the Green's theorem where under normal, despite the fact that the single integration looking more simpler, normally when we solve it we'll use the double integration. And then another thing is that the area enclosed for this part, it is literally just area enclosed by a line. And if you have seen the previous lesson, because we used the R as over there, so over here is also basically just area enclosed by R. So over here, after this lesson, you have realized that there's kind of a pattern other than this being one and this being different. For this lesson over here, we'll be solving for case 2 and 3. We'll be specifying on that. So for case 2, just like case 1, we'll be changing it from Cartesian coordinates to polar coordinates. So despite changing into polar coordinates, what doesn't change is that it doesn't mean that this will become a circle, okay? So most polar coordinates, normally you use it for circles and all, but yeah, you can use it for any kind of shape and area enclosed by a line. Once again, it doesn't necessarily have to be a circle, it doesn't need to be enclosed by a curved line, as long as it is enclosed by a line and so not like heavy intersections and all. So here what we're going to let is that we're going to let x be equals to r cosine theta and y will be equals to r sine theta. So what we're going to have here for this part here you have our case of x dy, and then x dy you change it to polar coordinates and you'll get r cosine theta d r sine theta. Now that we've got it over here, we can take out the r since it's just the coefficient. So here you have r squared. And what's going to be our boundaries? So our boundaries over here, fun fact, for this part had over here if you only put single integration without the circle, it is not an enclosed area, okay? Okay, so for this part, our boundary over here would be zero to 2 pi. Then over here 0 to 2 pi, and then when you take this out, you differentiate and they'll become cosine square. Cosine square theta d theta. You use the double angle formula, and what you'll get is so by using double angle formula, cosine square theta is 1 plus 2 cosine 2 theta. And this is what you're going to get. And over here in front, you have to have a over 2. And now moving on, while in front is still r squared over 2. Behind over here, we basically can integrate, where here you have theta plus sine half sine 2 theta ranging from 0 to 2 pi. Well, over here what we're going to have is when we substitute it in, so if we substitute 0 inside, what you're going to get will be sine 0, which is 0, and then if we substitute 2 pi inside, it becomes sine 4 pi, which is still 0. And now we can basically ignore that part since it's literally equal to 0. And now for the theta pi, if we substitute 0, it will still be 0, but if we substitute 2 pi, you'll get 2 pi, and thus over here you can simplify and you'll get pi r square. Okay, now you may realize that the area of the result we get over here is equals to that of a circle. However, just because the area of it is equal to that of a circle doesn't mean that the shape that the area is enclosed in is definitely a circle. Okay, it's just a random line that's enclosed, and that's one of the scenarios. Okay, and if you see the next one, you realize that over here for this part, under the circumstances of this, the result you're going to get is going to be 2 pi, pi r square. And now moving on to case 3. I'm not going to write this part down since it's just the same thing, polar coordinates, where I'm just going to add this on. Theta is from 0 to 2 pi. So over here, okay. Now moving on to our third case, what we are going to have here is y dx plus 2x dy. And then we substitute it inside again, 0 to 2 pi, or sine theta. So for this step, you simply just substitute. Okay, now over here, once again, we can take out all the r's from the d, and then we will have the r square outside. And then here we can also take out the sines and cosines from within the d, where you're going to have negative sine square theta plus 2 cosine square theta. Now what we can do over here is that, so what is his negative sine theta equals to? Sine square theta equals to. So technically speaking, you can use the sine square theta plus cosine square theta equals to 1. And what we are going to have here is, so negative sine square theta, it will become cosine square theta minus 1, right? So cosine square theta minus 1. And now moving on over here, you can integrate it and you have this negative 1, which will become theta. And then for this behind part, we can once again use the double angle formula. Then over here for this part, what we're going to have over here would be, so this you have negative 2 pi, so you have negative 2 pi r square, and then over here the front for this part, you can substitute it inside, where you're going to have plus 3r square over 2, and then integrate it and you'll get theta plus cosine 2 theta will become half sine 2 theta once again, and then from 0 to 2 pi, and to be honest, if you realize these two are just the same case. And then for this part, once again, sine 0 is 0, sine 4 pi is still 0. And then when you substitute theta is equal to 0, it's still 0. Theta is equal to 2 pi, it will be 2 pi, and thus we can simplify it while putting the positive side in front. So it becomes 3 pi r square minus 2 pi r square, which is equals to pi r square once again. And if you actually draw this out, it probably won't be a circle. So, but still, it has the same area, it's still the same as that of a circle. So a few patterns you may realize from these two lessons is that, number one, the difference, so yeah, obviously this is what we assumed, partial q, partial x minus partial p, partial y is equals to 1. This double integration d theta, you can change it however you want as long as it follows this rule. And if that is so, the result you're going to get is always going to be pi r squared when you use polar coordinates. Okay. Alright, so that's mainly it for this lesson. Just take a quick look. Okay, so that'll be all for this lesson. Last but not least, thank you for your watching.